Hello, I'm Dr. Tom Meixner. I'm a professor at the University of Arizona in the Department of Hydrology and Atmospheric Sciences, and I work on how sort of the infrastructure, particularly green infrastructure that we build in cities to allow water to pond and infiltrate, affects urban hydrology and affects water quality, and enables us to access a water resource we wouldn't otherwise be able to access. I'm joined by Dr. Margaret Garcia and Giuseppe Mascaro to discuss urban hydrology. Would you like to introduce yourselves?
Hi, everyone. I'm Dr. Margaret Garcia. I am an assistant professor at Arizona State University, and my specialty is water resource engineering and how the design decisions we make for our infrastructure systems impact their performance, particularly when we're operating under changing conditions.
Hello, my name is Giuseppe Mascaro. I'm also an assistant professor at Arizona State University in civil engineering. And I study precipitation extremes and their impact on infrastructure in urban areas and how they're going to change with climate change.
Cool, thank you. So to get started, what is hydrology?
So hydrology is the science that studies the cycle of water, or the hydrologic cycle. You may know that the volume of water on Earth is the same now as it was when the dinosaurs were on the Earth. To give you a number, it's about 1.4 billion cubic kilometers. What does it mean? It means that if you take our planet, the surface of our planet, and you put 10 feet or about 3 meters of water on top, that's the whole amount of water that we have. Now, most of it, about 97%, is in the ocean, and the rest is fresh water that we use. This volume includes all phases. So the liquid phase in oceans, rivers, and lakes, the vapor in the atmosphere, and the solid phase in ice and snow. Now, this water is stored in reservoirs. The main reservoirs on Earth are the Earth's surface and subsurface, the atmosphere, and the oceans. And water moves from one reservoir to the other. That's why we have a cycle, and this is done through forces that come from the sun. So the solar radiation that promotes evaporation and mixing of vapor in the atmosphere, and through gravity. Okay. Now, each of us has seen water movement. For example, looking at rainfall, there is a water movement from one reservoir to the other, and you have seen pasta boiling, so there is a movement of water also in that situation. Now, these movements are called water fluxes, okay? So water moves from the Earth to the atmosphere through evaporation from water bodies, for example, from lakes, from oceans, or from wet surfaces in the vegetation and soil, or through transpiration, because plants have roots that are able to extract water from the subsurface. When this happens, there is a change of phase from liquid to water vapor. Now, once the water is in the atmosphere as vapor, it can travel long distances thanks to differences in pressure and temperature, and depending on local conditions, it can condensate or it can freeze, leading to precipitation in form of rainfall, clearly, snow or hail. Precipitation falls on land or oceans. When it falls on land, it can be intercepted by vegetation, it can infiltrate in the soil, or it can become surface runoff. When it infiltrates in the soil, it can flow laterally and it becomes subsurface runoff. It can evapotranspire, going back to the atmosphere as we discussed a second ago, or it can percolate down to the aquifer and become groundwater. Surface runoff travels on the surface of the earth, and then it reaches the rivers and it becomes stream flow and eventually discharges into the ocean. Groundwater also travels laterally until it reaches the rivers as base flow, and eventually it is discharged in the oceans. There is one area of hydrology that I would like to mention, which is relevant for urban hydrology, and it's called watershed hydrology. What is this? This is the science that studies these processes within watersheds or basins. These are physical regions, areas that drain to a given location, usually in a river. Watershed hydrologists have developed hydrological models, which are numerical tools that we use to predict flood, for example, from weather forecasts. The accuracy of this model relies upon the availability of data about the water fluxes, the water movement, and the water storage.
Cool. Excellent overview, Giuseppe. Knowing the background of hydrology, what does urban hydrology entail?
Urban hydrology, just like hydrology in general, studies the movement of water in the environment and the reservoirs where it's stored. However, there's some key differences in the urban environment. So in our urban environments, we have made substantial changes to the physical landscape as we built roads, buildings, we've changed landscapes, planted new types of vegetation, and all of these affect the movement of water and the storage of water in reservoirs. So when we have a precipitation event, like a rainfall event, in the urban environment, the movement of water through that urban environment now depends not just on the soil properties and the topography like it would in a natural watershed. It now also depends on the materials that we've used in construction, where we've built roads, and the small scale topographic features like curbs and walls and roofs that change the way that water flows by presenting either physical obstacles or impermeable boundaries, meaning materials that water can't pass through, like pavements. And so this, in some cases, this makes estimating and predicting the flow of water easier because the movement on surfaces that are 100% impervious, like pavements, can be easier to predict than a natural surface. But it also makes it harder to estimate and predict in some ways. And that's because the urban environment is very, very heterogeneous in space. So what this means is that as you move in space, as you're walking around a city or a suburban area as a pedestrian, the conditions change quickly in space in ways that matter a lot for the movement of water. There's different materials. You go from a concrete sidewalk to a grassy lawn, to a lot where there's many buildings, but then small impervious areas like little gardens. And this affects how much water infiltrates into the earth versus moves along the Earth's surface as surface flow. And then the other challenge is, in addition to this heterogeneity in space, water flows can change very quickly in time in the urban area because of how impervious the surfaces are and because we've built infrastructure to quickly move water out of urban areas to minimize our risk of flooding. So when water falls on impervious surfaces, one, it doesn't infiltrate, and two, those surfaces tend to be lower friction, so water moves more quickly across the surface. And we've built channels and subsurface pipe networks to move water quickly away from areas which it could be a hazard to humans that are either walking or driving, or to property like homes and hospitals, other infrastructure. And so this means that water moves quickly. So as a result of this, we need a lot of data to really understand what's happening in the urban environment. We need a lot of data in space to characterize the properties of this watershed. And we need a lot of data in time to be able to capture these changes that can happen quickly because the water moves so much more quickly in an urban environment.
So sounds like urban hydrology is a rapidly developing field with plenty of room to grow. How would you say urban hydrology has improved in recent years?
Well, urban hydrology is becoming a pressing need to study because of two main reasons. First of all, population has been growing throughout the world and moving to cities. So there is a concentration of assets and people that have to be protected. Secondly, we have this problem of climate change, which is huge in terms of probably increasing the intensity of precipitation extremes. And again, this will result likely in more urban flooding. So that's the reason why urban hydrology is very important now, an important topic to study. We have done some progress to improve our understanding of urban hydrology. First of all, we have done progress in the ability to measure precipitation and resolutions that are relevant for the systems that, as Margaret just mentioned, are very heterogeneous in space and where the processes evolve very fast, okay? So in the United States, there is a network of weather radars that are measuring precipitation at resolutions of about 4 kilometers 1 hour, which is unique probably in the world. And that helps a lot in understanding how this input, this water flux, is affecting the system, in urban areas. Secondly, we have problems in knowing high-resolution topographic information in urban regions that are needed to understand, for example, slopes of roads, slope of pipes, as well as we don't have knowledge of water infrastructure characteristics. This is a problem that cities may have because they have not digitized this information, or because they don't know it, because the infrastructure is old. There's been some progress thanks to remote sensing. For example, sensors called LiDAR are able to measure terrain high resolution, changes of terrain at high resolution, and satellite imagery is also a resource that we use to understand land cover high resolution in urban areas. That said, we still do not know much about the subsurface, what's in the underground, mainly pipe.
So how do advancements in urban hydrology help address the problems such as the impact of flooding on transportation infrastructure?
There's a number of ways that these advancements can help us better understand the processes for urban flooding, and with that understanding, better predict them. So give people useful information about how to avoid these flooded areas and how to better design to minimize flooding risks. And so as Giuseppe mentioned, the data component of this is pretty big. But we, as the hydrologic and water resource community, are developing a number of new ways to integrate these different data sources, of information about the surface, like LiDAR, that give us high resolution information about the watershed itself, and also designing new sensor systems that can help us understand the movement of water once it falls on the urban environment. One example of that is utilizing cameras in the urban environment to measure the amount of water that builds up on the surface. So when flooding occurs, we get a buildup of water on the surface, and our team is working in collaboration with computer scientists and experts in image processing to take photos of the roadway and the curb system, and use image processing technologies to estimate the depth of the water. And what that then gives us is how much flooding we have at points in space where we have a camera available taking images in real time. So this gives us a partial picture of what's happening in an urban area. Wherever we have a camera, we can then process that image quickly and estimate how much water is building up. And by taking those images and processing them frequently, we get a picture of the rainfall event. But importantly, we can leverage this information that's at particular points in the watershed by combining it with our understanding of the watershed properties, like the topography and the materials, the land use, and the infrastructure system, the networks of pipes and channels, and the way in which we understand the physics of water flow on the surface and then through pipes and channels, to use that information collected at points from the cameras to improve our models of the system. And so by pairing these different types of technological advances, we can get a much clearer picture of where and when flooding is occurring, and then are working towards being able to provide that information in real time or near real time to say, this is where it's flooding now, and based on forecasted precipitation, here's where it's likely to flood in the near future. And that's really the type of information that we all need as we're trying to navigate the urban environment and stay safe in a storm, not drive through an area that could be hazardous. And it's also what emergency responders need to both assist in areas where flooding may be a hazard and redirect folks away from those hazardous areas.
Well, thank you, Margaret and Giuseppe, for your thorough explanation of urban hydrology.